All right, so in our parent class, we're getting into a chapter on number theory. And number theory is very heavily concerned with properties of integers, whole numbers, things without fractions, decimals, that kind of thing. And one of the primary things that it's concerned with is factors, prime factorizations, and things that are related to those concepts. So what I wanted to do here is practice finding the prime factorization of a whole number and then using prime factorizations to find Gcfs and Lcms. So this is already stuff that's been covered. It's just kind of review of that material. Our first problem that we're going to work through is finding the prime factorization of 1,350. And the way that we're going to do this is we're going to use a factor tree, which was the technique that we did in the parent class. So the trick with the factor tree is to try and find factors of this number, and a good technique to use is to use the kind of different divisibility tricks that we have. So I notice, for example, that this number ends in a 0. That tells me right away that it's divisible by 10. Okay, so 10 is one possible factor that I could use. Dividing this by 10 simply cuts that 0 off, so that would give me 135. Excuse me. From here, what I can do is start breaking down either of these factors. So 10 is easy to factorize as well. 10 is equal to 2 times 5. And if you remember from these factor trees, anytime we get a branch that ends in a prime number, 2 is a prime number and 5 is a prime number, we circle those. You don't want to break that 2 down into 2 times 1, or this 5 into 5 times 1, because the 1s are not prime numbers at all. They don't help us. And if you were to do that, then this factor tree could go on indefinitely, because if you split this 2 into a 2 and a 1, then that 2 could be split into a 2 and a 1, and then another 2 and a 1. And you can kind of see how it just never stops. So we stop when we get to these prime numbers. Okay, so next what we have is 135. Now looking at this number, I can see that it's divisible by 5 because it ends in a 5. So I'm going to split that into 5. 5 times what? Well, let's see. If you were to divide this by 5, either with long division or just in your head, you should get 27 as a result, and you can verify that. This 5 is a prime number, but 27 is not prime, so I have to continue breaking that down. 27, I know, is equal to 3 times 9. 3 is prime, so I'll circle that one. And finally, 9 is equal to 3 times 3. Just barely had enough space for that. Okay, so once we have done that, the goal in finding a prime factorization is figuring out a way to rewrite the number that we're given, 1,350 in this case, as a product of prime numbers. And as we said in the parent class, we have this thing called the fundamental theorem of arithmetic, which says that any whole number greater than 1 can be written in exactly one way as a product of prime numbers, not counting different rearrangements of those prime numbers in the product. So looking at the numbers that I have here, the smallest prime number is a 2, and I only see it appearing one time. So that means 1,350 is equal to 2 times. My next largest prime number is 3, and I see it appearing 3 times. 1, 2, 3. So I could write 2 times 3 times 3 times 3. Of course, 3 times 3 times 3 is the same thing as 3 cubed, and that's a little bit more concise of a way of writing that. Finally, I see 2 5s appearing in my prime factorization, so that means that can be written as 5 squared. Okay, so again, that thing that I mentioned, the fundamental theorem of arithmetic, and what that says is that this product of prime numbers, 2 times 3 times 3 times 3 times 5 times 5, is the only product of prime numbers that will equal 1,350. There are no other products of prime numbers that will ever equal this number. And again, that's not counting, rearranging these. Like if I did 3 times 3 times 3 times 2 times 5 times 5, I'm not counting that as a different product than this. Okay. We have a couple of problems here now where we're finding Gcfs and Lcms. And Gcf, greatest common factor, LCM stands for least common multiple. In some cases, you don't really need to use prime factorizations to find these, because you might be able to do it mentally, so looking at these numbers, for example, the GCF, the greatest common factor of 18 and 24, I'm literally looking for the largest factor that they have in common. Okay, now there is the most rudimentary, most fundamental way of doing this is to just list all of the factors of 18, list all of the factors of 24, and then compare them and find the largest one that they have in common. Another technique that works is one that's taught a little bit less frequently than that. If you were to subtract these numbers, the larger minus the smaller, 24 minus 18, you would get 6. Now, due to a result in number theory, a very simple result actually, whatever the difference of these numbers is, in this case 6, the GCF of those two numbers has to be a factor of that difference. It does not necessarily have to equal this number 6, although it turns out that it does in this case. It just needs to be a factor. So what you do from here is you start looking at factors of 6 starting from the largest factor of 6, and then you ask, is that also a factor of 18 and 24? So remember, every number is a factor of itself, which means the largest factor of 6 is 6. And is 6 a factor of both 18 and 24? Well, it is, because if I divide either of these numbers by 6, I get a whole number. So that right away tells me that the GCF of 18 and 24 is equal to 6. So that's one of my answers. Now that little trick might seem really, really useful, and it actually is, but only when these numbers themselves are either relatively small or really, really close together. Because if the two numbers are really close together, that means their difference will be a small number. Small numbers are easy to check for factors in our heads. But if these numbers are really, really big or really, really far apart, this technique doesn't really help as much as it did in this case. So we're not going to use that technique all the time. It's just when you see a case where it would be helpful, that's when you want to bust that out. LCM of 6 and 9. I think I might have done this one in the parent class. I can't remember now, but this one is really straightforward and easy to do mentally. So for this, remember, multiples are different from factors. Multiples of a number are numbers that I get when I count by a particular number. For example, if I count by 6s, I get 6, 12, 18, 24, 30, and so on. Every number in that list is a multiple of 6. So there are infinitely many multiples of 6 because I can count by 6 without ever stopping. Same thing with 9. In this case, what I'm looking for is a common multiple in those two lists of multiples, 6, 9, 12, oh, I'm sorry, I don't know why I put 9 in there, 6, 12, 18, 24, and so on, 9, 18, 27, 36, and so on. I noticed that the number 18 is the first number that appears in both lists, which makes it the smallest multiple that these two numbers have in common, which is the meaning of least common multiple. So I can here say LCM of 6 and 9 equals 18. Notice that the LCM ended up being larger than both numbers, whereas the GCF in this example was smaller than both numbers. They don't have to be that way, but I could tell you that the LCM can never be smaller than either of these, and the GCF can never be greater than either of these. See if you can figure out why that's the case. Okay, in this last example here, we're doing a GCF and LCM problem again, and even though I could approach both of these the way that I did up here, it would be a lot more work, and that's simply because in this case, the two numbers that I'm working with are much larger and much farther apart than in this case, so that trick that I used wouldn't be as simple. And in this case, 77 and 110, I could find the least common multiple by counting by 77s and counting by 110s, which is not as easy as counting by 6s or 9s, so coming up that list would take a little more work. And the least common multiple also is going to show up further along in those lists than it did here. So that's not a very efficient way of approaching these problems. And so here's where we want to use the prime factorization idea. So starting with the GCF, I want to take both numbers, 1500 and 450, and I want to find prime factorizations for each one of those. So we'll do 450 right here. 1500, okay? I notice that it ends in 2 zeros, which means it's divisible by 100. Specifically, it would be 15 times 100. Okay? kind of, to me, the most obvious way to break that down. Now, you might look at this and you might have thought, instead of being divisible by 100, you may have thought divisible by 10. And you may have written 150 times 10, which is also correct. And I think I mentioned this in the parent class as well. When you're doing these factor trees, especially if the number has a lot of factors, there can be many, many different ways that you choose to start breaking that thing down into a product of factors. But ultimately, that doesn't matter, because no matter how you end up going through this process, you will always end up with the same set of prime numbers at the end of it. So you don't need to worry about, was I supposed to do 15 times 100 or 150 times 10 or some other combination? It doesn't matter. Your factor tree might look different from mine, but our end results should end up being the same. So let's keep going. 15 is 3 times 5. Both of those are prime. 100 I could write as 10 times 10, and each of these are equal to 2 times 5. Okay, so now looking at the factors that I have 2 2's, so that means 1500 is equal to 2 squared times, I have a 3 showing up, and that's the only 3, times 3, 1, 2, 3 5s are showing up in there, so I would write 5 cubed. Okay, we're going to break this down in a similar way. 450, to me, the most obvious way to break that down is 45 times 10. 10 is equal to 2 times 5, so we have that. 45, from my multiplication tables, I know that's equal to 9 times 5. 5 is prime. 9 is equal to 3 times 3. Okay, so that means 450 is equal to 2 times 3 squared times 5 squared. All right, now's the step where we want to find the GCF of these two numbers, 1500 and 450. So the way that we're going to do this is we use the prime factorizations, and what I'm going to do is look for not just the primes that these two numbers have in common, but how many of them they have in common. So for example, both of these numbers have a 2 in their prime factorization. This one has 2 2's in it. That's why it says 2 squared. This one does not. So they don't have 2 2's in common, but they do have one of those 2's in common. They each have at least one 2 appearing in their prime factorization. So I use 1, 2 in my prime factorization here. An easier way to remember that is when we're looking for the GCF, if we have prime numbers in common, we use whichever one has the lowest exponent and put that into our GCF. We think of this as having an exponent of 1, which is the smallest of those two, so I use that. Next up, I have a 3 and a 3 squared. Well, 3, or 3 to the first power, is the one with the smallest exponent, so I say 2 times 3. Next up, I have a 5 cubed and a 5 squared. Between these two, 5 squared has the smaller exponent, and so I use that. Okay? Now all that's left to do is to multiply everything out to see what the end result is. 5 squared is 25, 2 times 3 is 6, so this is 6 times 25, which is 150. Okay? And if you wanted to, if you're concerned that you may have done something wrong, one little, we call these sanity checks. One sanity check that you could do is see if this number actually is a factor of both of these. It doesn't necessarily mean that it's the greatest common factor, but it would at least point out if you did something horrendously wrong and got a number that's not a factor of one or both of these. So we already know 150 is a factor of 1500. We actually used that. Oh no, we didn't use that in our prime factorization, but 150 times 10 would give me that. 150 times 3 would give me 450. So with that definitely worked. Okay, LCM, we have another problem right here. And I'm going to do the same thing to start. I'm going to find a prime factorization for each of these numbers. 77 breaks down in one step. 11. It's 7 times 11. Both of those are prime numbers. Okay, 110 is also divisible by 11. It's equal to 10 times 11, and then 10 is equal to 2 times 5. So both of these broke down fairly quickly. To find the LCM, I'm going to do something similar. I'm going to write out my prime factorizations. 77 equals 7 times 11. 110 equals 2 times 5 times 11. I don't have any exponents on these guys. In a different example, I might, but in this case, I didn't, and that's okay. What are we going to do now? Oop, I've started writing the wrong thing. LCM, of 77 and 110. So this is going to be similar to the GCF in the sense that we're comparing the prime factorizations of these two numbers, but now I'm not looking for things that they have in common. What I'm trying to do is I'm trying to build a number such that its prime factorization has all of the primes that appear in this number as well as all of the primes that appear in this number. So what I'm doing is I'm comparing them, and if there are any primes that are in common, I'm going to choose the one with the largest exponent as opposed to the one with the smallest exponent like what we had here. If there are primes that are not in common, I still include those in my LCM. So for example, in this prime factorization here, I have a 2 and a 5. Even though there's not a 2 and a 5 in 77, I need to include those in my LCM. Because again, we're building a number that has all of the factors that appear in one or both of these. I also have a 7 appearing there, which needs to be in my LCM, even though it's not here. Now there's two 11s, but there's only one in each prime factorization. I'm not going to write 11 squared because we're not just throwing every single prime that we see into this. We're using the ones that have the highest exponents. 11 to the first power and 11 to the first power, those are both the same thing. They both have the highest exponent. So I just pick one and I use it. So that's 2 times 5 times 7 times 11. 2 times 5 is 10. 7 times 11 we know is 77. And 77 times 10 would be 77 with a 0 after it, or 770. Okay? And that's how you construct an LCM once you use the prime factorization. So this is the kind of stuff you're going to be doing on the assignment this week, and that's going to wrap up this video.